Okay, so this is a lecture for section 2.1 in our book, and that section title is Symbols and Terminology. And most of this lecture is truly that, just getting used to the symbols and terminology that we're going to be using in in this chapter. Okay, so the first thing that we want to start with is defining a set. So a set is defined as a collection of objects. And, you know, that can be a collection of any type of objects. It doesn't have to be mathematical symbols or numbers. It can be, you know, the set of hair colors or something like that. Okay. And then we say that the objects belonging to a set are called elements of the set. Okay. All right, now there is a certain notation that we use, and there's two different types of notation, really. We can use a listing notation. So when we list, it's going to look like this. I might have a set that has the elements 2, 4, and 6, and 8, and I literally just list them out. I just write them out. These squiggle brackets here are what we use when we are trying to use set notation. So squiggle brackets denote that we're talking about a set. And then each of these numbers are the elements in this particular set in the list method. Okay. We can also use set notation, which looks like this. And I think we'll just express this same set in set notation. So it's going to look like this. We have a squiggle bracket and then an X such that. So this X and this bar, we read that as X such that. And then for this particular one, we could say X is an even counting number less than 10 would be one way to represent that. Okay. Okay, so another thing that we can do with sets is we can give them a name. So we can give a set a name. For instance, let's say that I wanted to look at this set right here. It's certainly easier for me to talk about set A like this than it is for me to say, well, I'm going to look at the set containing the elements 2, 4, 6, and 8. I can identify this set as being labeled set A, and then I just have to say, I'm going to look at set A when I'm talking about it. Okay. Typically, when we are identifying sets with a name, it's usually a capital letter that we associate with it. Okay. We also have the set that actually contains no elements. So the set containing no elements is what we call the empty set. So the set that says no elements right there, the set containing no elements is what we call the empty set. Okay, now the empty set is not the same thing as 0. First of all, let me just show you the notation. There are two different notations for this. We can use just squiggle brackets with nothing in them, or we can use a 0 with a hash mark through it. Okay, either of these things represent the empty set. And so I want to go back and talk about this idea of 0. The empty set is not the same thing as 0. 0 is a number that actually has, you know, it's a number that has a quantity, if you want to call that, associated with, and that quantity is nothing. But the empty set is a set that contains no elements. So it's a different thing. It's not the same thing as 0. Okay. All right. Let's see. Another thing that we can do when we're working, that we often do when we're working with sets, is we use this notation right here. And I know you've seen it before. I can't remember what it's called, but it's this dot, 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 has a name. We can use this dot, dot, dot to either show the continuation of a pattern or to show that a particular pattern goes off towards infinity. Okay, so we can show the continuation of a pattern. So for instance, let's just say that I was talking about having a set A that went like this, 2, 4, 6, 8, and then it continued, but maybe it ends at 50, and I don't want to write all those even numbers out. So we can just use the dot, dot, dot to denote, that we're going that same pattern all the way out to 50. I could also be talking about a set that, maybe doesn't end. So maybe it's all of the even numbers on out towards infinity. So my dot, dot, dot would just show that. Okay. All right, another symbol that we use is this symbol right here. It looks like an E, but it's kind of curved. So it doesn't have the, a regular E in our alphabet looks like that. This E is curved around the ends. Okay. And this is the symbol that denotes that something is an element. So this is the symbol used to denote the word element. And that's helpful because it looks like an E. So, okay, so just if we use, for instance, this set A right here, I could say that 2 is an element of A. And mathematically, this is correct, and I'm saying that 2 is one of the elements that exists in this set. We can also use a hash mark through the element to say that something's not an element of a set. So for instance, again, if I'm looking at this set A right here, I could say 1 is not an element of A because it's not, doesn't exist in that set. Okay. All right. The next thing I want to do is go through the set of numbers with you because it's relatively important when we're talking about sets that you understand each of the classifications of our real number system. Okay, so talking about the set of numbers here. And the first one that I want to talk about is the natural or counting numbers. So you can either refer to them as the natural numbers or the counting numbers. That set is the set of these numbers, 1, 2, 3, 4, and on out towards infinity. Okay, so just basically all of our whole numbered numbers that we use to count. The set of whole numbers is the same set as above, but it also includes the number 0. So we have the number 0, 1, 2, 3, 4, and then on out towards infinity. Okay. The next set of numbers is the integers, and the integers include 0, the counting numbers, and then also all of the negative numbers. So we come in from negative infinity. We have our negative numbers, our 0, our positive numbers, and then we go on out towards positive infinity. Okay, the next set that we want to take a look at are the rational numbers. And I'm going to give you the formal definition for rational numbers, and then I'll kind of decipher it for you. Okay, so our formal definition looks like this. This is the set of P over Q such that P and Q are integers and Q is not equal to 0. Okay, so Q obviously can't be 0 because Q is in the denominator and we can't divide by 0. P and Q are integers here, simply saying that if you take any two integers and you divide them, you're going to be talking about a rational number. Okay, technically what this is, or I guess this is the technical part, but to decipher that for you, rational numbers are basically terminating or repeating decimals. Okay, so terminating or repeating decimals are what are classified as rationals. Okay. Next classification, and the last one we're going to talk about for the moment, is the irrational numbers. Okay. The irrational numbers are x such that x is an element of the real numbers. When you see an R like that with a line down the middle, that means the real numbers. And the real numbers are basically all of this together. I'll draw you a picture here in a minute. So x such that x is an element of the reals, and x cannot be expressed as a quotient of integers. Okay. Now, technically, that's probably not going to make a lot of sense to you, but this x cannot be expressed as a quotient of integers. This quotient of integers things, that's a rational number, right? So this is basically saying if it's a part of the real number system, but it's not a rational, then it's an irrational. And this tends to be our non-terminating, non-repeating decimals. Numbers that fall into this category are some of our special numbers. Pi falls into this category. Some of our square root numbers, for instance, the square root of 2, etc. There are some special numbers for us that fall into this category. Okay, so just to give you an idea of how all of these relate to each other. So remember that we have the naturals, the whole numbers, the integers, the rationals, and then the irrationals. And if we were to draw this real number system, all of this comprises the real number system. Okay. And the real number system, we can divide this up so that it looks something like this. We have our irrationals over here that have nothing to do with the rest of this real number system. They are separate. But then we have our rational numbers. And, this idea of a subset starts to play out here because our integers are actually a subset of our rational numbers. And the whole numbers are actually a subset of the integers. And the natural numbers are a subset of the whole numbers. The way I always like to explain this is, I don't know if you've ever seen those Russian dolls where they have a doll inside another doll. You take the outer doll, you take that lid off, and then inside you see the exact same doll that's a little bit smaller, and then you take that lid off, and that's kind of how I think about this. This is kind of like the doll inside of a doll. It's a subset idea. Okay. All right. So next definition that we need to go over is this idea of cardinality. When we work with sets, we are concerned with, often we are concerned with how many elements are in the set, and that is what is our cardinality. So we can refer to it as the cardinal number or simply the cardinality of the set. Those are the same thing. Okay, so the cardinal number or the cardinality, this is the number of elements in a set. And we have a notation for this. We use the n, and it looks like this, n of a. So like, for instance, if we're talking about set A, and I want to know the number of elements in set A, this right here represents the number of elements in set A, which is the cardinal number. Okay. So maybe we should write that out. This represents the cardinal number of set A. Okay, so just to give you an example there, let's say that we have the set A that looks like this: 1/2, 1/3, 1/4, and 1/5. And if I asked you to find n of A here, n of A would be, we have 1, 2, 3, and 4 elements. Doesn't matter what the value of the elements are. I'm just concerned with how many elements I have when I'm looking at cardinality. So n of A here would just be 4 elements in that set. Okay. And the empty set, I should just mention this, the empty set has a cardinality of 0. Oh, that's not A, sorry. The empty set. Cardinality of the empty set is 0. In other words, it doesn't have any elements, which we've already talked about. Okay. Oops. That's right there. All right, so let's talk about finite and infinite sets. So I'm hoping that these words, you either understand these words, you've seen them before. The word finite means that we're talking about something that is countable or contained, or, you know, it is something sort of within our reach, I guess is how I could define it. Infinite sets are, we're talking about infinity, so something that goes on forever and, you know, is not, well, I shouldn't say it's not countable. Something that we can't find the cardinal number for. Okay, so let's just define these. A finite set occurs when the cardinal number of the set is 0 or a counting number. Okay, so in other words, you can find the cardinality for a finite set. Infinite sets, on the other hand, infinite sets occur when you cannot find. Let me actually say you cannot finish counting the set. Okay, and that's because, you know, if you're going towards infinity, you're going to keep going, and you're never going to be able to finish counting it. Okay, so that's the idea of an infinite set. And just to show you the difference, this right here, whenever I write EX, that means example. This is an example right here of a finite set, something that might have the elements 6, 12, and 18. This is finite because I can count its cardinality. It has a cardinality of 3. Versus something like this, maybe I could use the example from earlier. This is something that is infinite. It's going off towards infinity, and I can never finish counting that. Okay? All right. And the last concept here is the concept of equality. So we need to understand, when we're talking about equality, that the word equal and the word, excuse me, I'm looking at my notes. The word equal and the word equivalent mean different things when we're talking about sets. Okay, and we need to define this so that you understand this. So we say that a set A is equal to set B, provided the following two conditions are met. Okay? Has to meet these two conditions in order for them to be equal. This is what we're looking at right now, is this idea of equality. Every element of A is an element of B. That's one condition. And also, every element of B is an element of A. Okay? If both of these two conditions are met, then you can say that two sets are equal. Now, that's in distinction to this idea of equivalence. When we talk about equivalence in sets, two sets are equivalent if they have the same number of elements. The elements themselves don't have to be the same. They just have to have the same cardinal number. So we say that two sets are equivalent if they contain the same number of elements. They don't have to be the exact same elements, just the same number. Okay. So just to give you an example here, this set A, let's say I have set A here that has the elements 1 and 2, and I have the set B that has the elements 3 and 4. I can say here that A and B are equivalent. And the reason they're equivalent is they both have 2 elements. Okay? But A and B are not equal because in order for them to be equal, they need to have the exact same elements. So 1 would have to be an element here, 2 would have to be an element here, and vice versa. Okay? All right. I believe that is most of our background information here for this section. So take a look at your homework and email me if you have some questions.